Hey there, everyone. Welcome to Chapter 11. So, this chapter almost exclusively deals with what's known as angular momentum, all right? Which, as you may suspect, deals with an object in motion, right? If you remember back to Newton's first law, an object at rest tends to stay at rest, and an object in motion tends to stay in motion, right? In both of those cases, unless an external force comes along and acts on it. Well, in Chapter 11, we kind of take that one step further. And now we have an angular component to it. Now, that doesn't always mean that objects have to be moving in a circle or moving in an arc to have angular momentum. What that means is that if we choose a point in space to measure from, there's a displacement relative to the velocity that the angle is measured from, right? It's okay, just let me show you what I mean. Okay, so say, for example, we have a particle in space moving with some speed v, okay? And that particle is of some mass, yeah, sure. Now, that object, because it's moving with a speed, right, or a velocity, it has a linear momentum, which we write that as lowercase p, and that's equal to mass times velocity. Sure. Now, where does the angle part come from? Well, we have to choose a reference point to measure from. And you might ask, well, how do we know where to measure from? And the answer is, you just choose it. Just pick one. Doesn't matter where, just pick it, right? I'm going to pick right there. I'm going to call that point Q, okay? That's wherever, it doesn't matter, right? Wherever in space. Now, from that point that you just chose to wherever that object is at a certain time, that's known as the displacement, right? So we call that r. Now, if I were to translate r up along that line, the angle in between r and v is theta, right there. Remember, put those vectors tail to tail. And this is the angular momentum, right? Notice the object isn't really arcing. It's actually traveling in a straight line. But we have an angle because we chose a reference point kind of off axis, right? But that's okay. It's totally allowable. There's certain circumstances in which this specific strategy, right, or this specific method will be most effective. So let me just define the angular momentum real quick, okay? So if this is at one point in time, that object a little bit later, maybe over there, I'm going to say it keeps the same velocity, right? It doesn't slow down or speed up. However, you may notice that the displacement vector will be different, right? And you'll be right. So now it's a different r, which means that it's also a different angle. And because of this, the angular momentum as measured from point Q will change. Okay? So we define angular momentum as that displacement, in other words, the radius, which is the distance from the reference point to where the object is. We take that and cross it with the object's linear momentum. Okay? So I'll say this is one way to write the angular momentum. We'll see the other way coming up shortly, okay? For sure in later example videos. But this is one way to define and solve for an object's angular momentum, okay? So if you were to take the magnitude of this, by the way, that's where the angle comes into play. The magnitude of the first vector is just r. Magnitude of the second is m times v, the speed now, and sine of the angle in between. Okay? So if either of these, if any of these, r, m, v, or theta change, then overall the angular momentum changes. If they all remain constant, then, well, L doesn't change, right? In the case I've just drawn here, theta changes and R changes, so the angular momentum overall changes. And we'll see that when the angular momentum changes, there must be an external torque, okay? So let's go to the next slide and let me show you why, okay? So with an example to show both of these cases, we can take the Earth around the Sun. Okay, here's Earth's orbit. We can draw Earth in it if you want, right? Let's do, I don't know, Earth is up here. There's Earth. Okay, so as Earth revolves around the Sun, let's say it has some tangential speed, or its linear speed, v, okay? Yes, it also has an angular speed, omega, but for right now, let's just use v. What if I wanted to measure its angular momentum? Well, that means we have to choose a reference point, right? It can be anywhere in space, remember. It can be right here. It can be, well, measured from Earth. It can be measured from the Sun, or it can be measured from some point in its orbit, right? So let's do that. I'm going to choose a point in its orbit, okay, just for the purposes of this video. So I'll call that point Q again. And that means that we have a displacement vector of right there. I'm going to call that RQ, right? RQ. So the angular momentum as measured from Q, in this case, is defined as RQ cross P, right? Which we know is RQ cross mass times velocity, right? And as Earth revolves around the Sun month after month, year after year, its speed pretty much stays constant, right? Earth's orbit is pretty close to circular. It's not exactly circular, but for, again, the purposes of this video, it's pretty much circular, right? So it has the same speed over there. Well, we have a different radius. We have a different displacement vector, right? But also, what I didn't write is that we also have a different angle, right? Remember, there's theta there, and over here, whoa, theta is greater than 90, right? Well, when Earth is down here, point Q isn't changing, so V still there. Well, now R is, well, right here. So again, we have a different theta. So what I'm trying to get at is that now the angular momentum changes. Okay? So let's see what that looks like. We can write that as dl dt, right? The angular momentum continuously changes in time. So let's see what happens to the cross product. That means the following. It's the time derivative of R cross mv. All right? So this time derivative of a cross product, if you don't know, it's pretty much like the product rule, which means it's dr dt crossed mv plus r crossed with d, let's bring the mass out, crossed with dv dt. Okay? That's what the derivative of a cross product pretty much is, right? Now, let's see what happens. What can we cancel out? Well, let's see here. What is dr dt? That's a change in distance over a change in time. Change in distance over change in time. distance over time. That's a speed. That's a velocity. So really, this first term here is v, right? That's the rate of change of the length of this r, the vector, right? So when Earth is at point Q, r is 0. So dr dt is 0. And then as it moves around here, the length of r increases, right? So that's what that term right here is showing. But it doesn't matter that that's not the same as the tangential speed. It's still a speed. And that's what we have here. And with the cross product, if we cross the same vector, v cross v, that goes away, right? That's 0. So we're just left with the second term, or the second cross product. All right. So I'm going to actually recombine this second term into P. Okay. And so what we have ultimately is R cross dP dt, right? And that's equal to dl dt. All right. Now, what is dP dt? Remember back to impulse momentum, right? The impulse is force times time equals a change in linear momentum. Hey, look at this. What is P over T? That's a force, right? Doesn't matter if it's T or a delta T, that's a force. So that means that we can write this as R cross the force. Okay, what force, you may ask? Well, on the Earth, it's the only force applicable, which is the gravitational force from the sun. Okay, but the important thing is that there's an external force on the Earth. Okay, and so that gives us an external torque, right? And specifically write that external. And so this is where the change in angular momentum comes from. This external torque term, which comes from the force of gravity on the Earth from the sun. Now, we haven't studied gravity yet. That's chapter 13. But this is where, if the angular momentum is changing, it has to come from some external force. And in the case of the Earth around the sun, it's the gravitational force. Okay? So now, in any other case, there's a torque present whenever the angular momentum changes. Okay? So, the other case, if the angular momentum does not change now, well, instead of putting the reference point at Q here, let's put it at the sun, right? Let's put it in the very, very center. And I'm going to put it down here, okay? If I put now the reference point at the very center, we'll call that point C for center, okay? Now, I'll do that in, let's do it in red. Now, the radius is r. Assuming the Earth's speed in its orbit is not changing, what's the angle in between r and v? Right? Let's actually put Earth up here. If Earth is there, we have a velocity, we have a radius, r. If I move that up, we see that's pretty close to 90. In fact, it should be 90 if I draw my thing to scale, right? So now, the angular momentum as measured from point C at the center is this, right? It's the same as above, but the angle does not change, right? The angle is not changing now. And so what we have as far as the magnitude goes is simply r, right? The radius of the orbit times mv and sine of 90, which is 1. And so regardless of where the Earth is, the angular momentum now will always be r times m times v. There. So now delta L, as measured from the center point C, is 0. It's the same wherever Earth is. If Earth is now over here, traveling with some speed v, r is over here, right? And again, the angle should be about 90, which means that its magnitude is again rmv. And so now we call this conserved. The angular momentum is conserved if it does not change in time. If it does change in time, we say that's not conserved. Okay? So, whenever there's an external torque present, changing the angular momentum value, well, thus it's not conserved. Right? If it's always the same, it is conserved. So I hope this video has given you a little bit of an insight into what angular momentum is, and in that it purely depends on where we measure from. Right? That's the thing. It depends on where we measure from. Right? So, thanks for watching.